Well, the name of the software, our prime finite element program software, Dana, is coming from two words: displacement analyzer. So that's how the name of Dana formed here. And it's a general finite element analysis program which specific and special focus and implementation towards various types of civil, geotechnical, and oil and gas applications. So I emphasize on this part because there are many applications and say software products are available in the market. However, the advantage of using Diana towards civil and geotechnical application is existence of the variety of the material model dedicated for these type of applications and element types, including the assembly of all these concepts in a generic workflow and customized workflow for different applications. So this is very important, that the platform that Dana offers is very stable, very powerful, very user-friendly, including extra capabilities with respect to the civil and geotechnical and oil and gas applications. The core value of the company, if I want to highlight in this graphical demonstration, we are proud to deliver a world-class product to the market, and most of our clients are acknowledging this by feedback that they give to us. But this is only possible by, say, satisfying a very friendly and good teamwork with my colleagues from the development, from the administration, from the support, all the people who are working in Dana FEA. So we have a very nice and friendly and cooperative working environment. We all come with this mindset that we need to deliver the state-of-the-art technology in the release of the products that we have in our company. So Dana always comes with the latest developments, latest technology, latest modules that are available in the market. The core value that we have is based on the trust with our partners. So we always try to work with our clients, our partners, to make them feel successful in their project, competitive in their project by using our product, by using our service. And we always look for long-term relation with our partners. So there is no, short-term, kind of a small business talk and next step. So we always work on a long-term vision, long-term collaboration, and our partners always consult with us, and we offer them the solution that they offers, or we can kind of work together to customize based on their challenges. The quality that we have at different levels are quite pronounced. One is in the development, at the development level, based on the variety of the test checks, automatic checks that it conducted every night, because it's, we are a kind of dynamic company, and every day there are new developments and enhancements are incorporated in a version that we are planning to release for the next year. So therefore there is always ongoing checks, and also we do a kind of a regression test to make sure that the new developments are in line with the accuracy and the quality of the confirmed and verified and validated results. And also the environment that we are working in the company and with our basically clients is very dynamic and based on the innovative ideas, because the market is very dynamic, and the way that engineers these days are tackling to the projects is different from 5 years ago, and we need to be at least 5 to 10 years ahead to make sure that our clients, when they work with us, they have some sort of secure time frame in order to take advantage and, as I mentioned, be competitive in the market by using Diana. A little bit Well, there are many, so I tried to kind of summarize them, but here you can see some of the names associated to our valued clients. There are a variety of them, from consultants, from the contractors, from the government organization, from the university and research organizations, energy, green energy and energy fields, oil and gas. So there are a variety of the big names in the world of engineering can be seen in this slide, likewise here. And they're international because we tackle them all from our headquarters and with help of our partners in other regions that we have. So let's touch bases of some of the applications that we have, starting from the geotechnical and tunneling. Dana provides a complete solution for the complex type of, from simple and complex type of geotechnical applications, because these days, due to complexity of the construction zones in urban areas, so there is always a need and urge for modeling and simulation of the geotechnical application tunneling in 3D environment. Therefore, in the platform and the environment, you can model both 2D and 3D in one harmony, in one unique platform. And you can simulate different types of tunnel and underground structures based on different tunneling techniques. So it could be NATM, TBM, or just a normal excavation. We have a ground freezing analysis based on the three-phase analysis. This is a very unique solution that we offer in conjunction with the excavation of the soft soil or sandy material zone to, say, solidify the zone of excavation. A complete nonlinear SSI analysis, soil structure interaction analysis. So that's another powerful feature of Dana, that you can incorporate the structural failure as well as the geotechnical and the soil failure and interact them through the real nonlinear material behavior of the interface between. Then we have a concept of groundwater flow or seepage analysis, deep excavation and using temporary structures or supporting structures, PIRA foundation based on the different techniques that we have, and our pile element, which is a kind of embedded element, including the pile tip. You can use Dana in the context of geotechnical tunneling, mining for the earthquake, blast, and vibration analysis. You can consider the drain or undrained behavior of the soil. You can use Dana for embankment and consolidation, check for slope stability in conjunction with earthquake. So you have seismic analysis and you want to see the stability of the, say, your model throughout time steps. That's a fully coupled implementation that we have in Dana. You can take benefit of that, and many more that we can go through them as we go through the presentations. With respect to the reinforced concrete and young hardening analysis, Dana has a unique solution all over the world because we cover the whole process of casting, curing, serviceability, and failure, say like forensic type of analysis for reinforced concrete structures. These reinforced concrete structures could be steel and say rebars or fiber reinforced materials. These fibers could be steel or synthetic material, no problem at all. Therefore, you can model all types of concrete box girder, could be pre or post tensioning, composite structures, the interaction of the maybe steel and concrete, fiberglass and concrete, or different type of materials, new materials. You can use Dana for concrete dam structures because of the, say, the capacity and the size of casting, curing, or the whole process of like RCC dams that is needed for the hydration check and the kind of compaction. You can use Dana. We offer all the necessities in terms of material model, in terms of analysis types, and in terms of the output that you need to consider for the checking. We offer a series of design check tools based on the Eurocode for the reinforcement. We have a mobile load and design load generator, and also cross-section capacity check based on basically model code. These are some of the design check tools that we offer that can go along with the design and say checks for the industrial floors, for the slabs, for the beams, for the walls, for shear walls, for many type of, or for the bridge structure. That's very important for the bridge models. So you can use Dana for various type of application and take benefit of our design tools. For those who do not want to enter into deep nonlinear setup, material models, and analysis, we have a kind of simplified nonlinear analysis. We call it linear sequential analysis. So based on the degradation of the stiffness of the model as it goes through the failure, Dana basically deals with the, semi-nonlinear response of the model. You can use Dana for thermostress analysis or say young hardening or the heat of hydration analysis or early age behavior of concrete cracking. So that means you can monitor how these adiabatic curves can be introduced into the system, how the heat generates in the model, how these gradients develop in the core and towards the boundaries, and how these expansions are causing some sort of failure and the cracks in the concrete. Cooling pipes, you can use them to control this development of a temperature, crack initiation and propagation. That's a powerful tool and one of the key aspects of using Dana in conjunction with the structural analysis to not only identify the initiation and propagation and the peak failure, also post-peak failure, how the model goes through softening, how from the normal crack goes to crushing and the complete failure. And also you can combine these type of analysis with the fire, so the impact and effect of the fire on the model. For masonry and historical construction monuments, Dana has a very good reputation in order to combine the material models associated to the masonry structures or different type of analysis associated to historical and monuments in terms of performing nonlinear pushover analysis, in terms of time history analysis, in terms of damage and crack analysis. You can consider all those aspects in conjunction with Dana program. For dams and dikes, Dana has a unique solution in order to cover all aspects associated to various types of dams. And this comes because of the soil structure interaction, coverage of material property for the foundation and the soil and rock and modeling the faults, and also the superstructure and the main body of the dam, spillways, the gates, everything. You can model them and you can incorporate them with the unique features and analysis associated to the fluid structure interaction, time history analysis, linear or nonlinear, and also induced damage or failure or hydrodynamic pressure that are acting on the structure. For fire analysis based on the model code or based on the user-defined input, you can perform a fully coupled thermostress analysis and identify how the effect of, I give you example, for instance, fire in a tunnel or fire in a building for 2-3 hours, how this could cause a progressive failure in the structure. So some of the key and important infrastructures need to be checked versus some sort of reference curves from the RWS or other references that are known, and check the overall stability of the structure in case of fire. For earthquake and seismic analysis or dynamic analysis, Dana has a worldwide recognition, and that's because of the coverage of different type of solutions that we offer in terms of the linear, non-linear, hybrid frequency time domain if your model is subject to the or introduced into 2 domains, and also fluid structure interaction and liquefaction. For some advanced applications, Dana also has a good position, especially with the big players in this field, in the oil and gas, for simulation of the reservoir and the borehole stability, reservoir depletion when you extract the gas or oil, and how this substance of say collapse could happen. Casing integrity, and also cement formation. Plus, for the nuclear structure, because of the nature of these type of structures, subject to the high temperature gradient, subject to soil structure interaction, pre-stressing, post-tensioning, and also seismic analysis, Dana also widely used in these advanced type of structures with their own confidentiality and aspects of the technology that they have. The environment, now we have the latest version 10.4. It's become much more user-friendly as ever that you were thinking. So the environment is very interactive. We have a kind of a console for the inspection of your model at the geometry level, at the mesh level, with reference to the geometry components, loads, boundary conditions, functions, and the connections. We have a property window for quick and easy assessment of the assigned properties to the geometry, material, functions. Depends on your selections from the upper harmonica windows. In the lower part, we have two windows. One is the Python window, another one is the interactive window. The Python window enables you to communicate, to write, to script, to load, to read the corresponding script that are associated to your ongoing model, or if you want to do some parametric analysis, load the Python script, you can modify and manipulate it in this window. And message window helps you to read some error messages, some convergence information, some messages from the kernel, from the solver. All those information are reflected in the message box. And on the right hand side, you can have access to your analysis setup or the post-processing output features that are available in terms of the components or in terms of the deform, undeformed. So I try to go through them in one of the demos. Just quick update on the engines that we use. We use the Parasolid engine as our modeler, and we use some sort of CAD readers in order to interact with other geometry modelers. So if you have a model in AutoCAD, Revit, you can use our CAD reader and import everything in Dana and proceed with the rest of the model. Our mesh engine is one of the, CM2 is one of the powerful hybrid mesh engines that are available in the CAE industry. We have adapted that, and basically you can use a hexadominant or tetradominant or quad dominant for meshing your model. For load and boundary conditions, we offer a huge range of loads and boundary conditions that are applicable over the various type of geometry. Could be surface, edge, point, load, body, and also all the information which can be exchanged or interacted with Excel in a tabular format can be nicely communicated through the corresponding dialog box in Dana. For post-processing, we have a complete set of post-processing tools in order to generate the contour, vectors, clip plot, section plot, and the tabular output, diagram output, so we can highlight them later in the slides. Our material models classified into type and material model in order to classify if you're dealing with, for instance, soil, if you're dealing with steel, if you're dealing with the masonry or concrete, and based on that, class, the corresponding constitutive models will be available under the drop list, and you can choose which constitutive model you want to deal with. The load combination table is available in order to define your load combinations based on the different model code, or if you have several loads and you want to see the impact and effect of that based on different combination, you can introduce them in the load combination dialog box. The functions that we have, these functions are available based on a special and non-special function that can be incorporated at a different level, at the geometry level or at the material level, in order to define and set up your final analysis setup. And indeed, the analysis windows, especially for instance for the construction stage or phase analysis. This is very interactive based on the active, deactive, and say duplicated work environment. You can nicely have overview about the sequence of your model. The workflow that we have in Dana is based on the geometry. So mesh is kind of a secondary concept in Dana. So everything deals or set up at the geometry level in terms of the introducing and definition of the model, importing that or creating, assigning the properties, loads, boundary conditions, everything when it's set up. Then you generate the mesh, you set up the analysis, and you run the model. So therefore, because everything is at the geometry level and it's at and the assignment of the properties and the dimensions, it makes it more say it flexible and easy in order to combine it with the Python scripting and make it parametric analysis, modifying it, alter it, and redo the whole analysis in a kind of a iterative procedure. In terms of the creating the geometry, there are many tools and options are available. I quickly go through some of the key and main aspects of them, starting with interacting and exchanging the model with the third party. So if you have some models from CAD, SolidWorks, or Revit, or Rhino, you can just make the DXF, DWG, STEP, IGS, or IFC and import them into Dana. And in Dana, you can use the Parsolid tools and interact and exchange them together. For IFC, as I mentioned, you can use that from the Revit, and you can directly import that. And also, if you have a cloud of nodes, you can use our, say, Bezier surface generator, and you can import the cloud of nodes, and then automatically generates a three-dimensional surface for you. After importing and bringing this geometry in Dana, you have a geometry check tools, and based on that, Dana identifies series of, say, typical geometry faults that might be inherited in the model from the origin, and these features can be, or the deficiencies can be identified, and based on our tools, you can fix them. That's a very good and powerful tool that in Dana you can identify and fix them. Or you may have a strategy to create your geometry and model in Dana based on the primitive features that we have in terms of creating 3D model, 2D, 1D, and say line or point. So these are all the available and generic type of modeling tools that helps you to create your model. Moreover, you can interact and intersect different parts based on the Boolean operation, based on the transformation, based on the sweep function along the guide curve. This is very powerful because if you want to come up with the solid model and you have one only uniform cross-section, you can define your cross-section in 2D, or you can import this cross-section and sweep it along the reference guide curve. And then it generates a nice solid model for you that you can easily proceed based on our extrusion measure and have very nice and smooth elements distribution along this model. In addition to the sweep, we have lofting operation at the geometry level based on the different criteria and the different methodologies that helps you to come with the complex shape based on the minimum reference geometry, and you can generate your model in a kind of three-dimensional environment and proceed with your analysis. This could be from a double arch dam, or this could be some sort of a twist and tweaked shapes that you may consider in your model. Our smart filter for selection enables you to identify and select the corresponding geometry components or element sets, mesh sets, nodes, or series of specific types of elements and sets like anchors, reinforcement, piles, and sheet pile walls that are available in the model. So based on the corresponding filter, you can nicely and easily select those selected items in all over the model. Since we are using the Parasolid and optimize that with our mesh engine, then automatically identifies the automatic clashed part. Therefore, this feature enables and assures you in terms of the nodal connectivity. So this is very important in terms of the continuity of your model in the finite element analysis. So any Boolean operation data, it always assures you, or matching faces and the bodies with respect to each other, always assures you that there will be a common nodes and faces during the analysis. So you have a kind of homogeneity in the analysis. You can sew two faces or several faces and make a kind of uniform shell out of series of sheets, or you can explode them, convert the bodies into the closed sheets. In order to define the load or boundary condition, there is one important factor that you need to consider, and that's always you need to imprint the position of your load or boundary in your model. So imagine from the top, if you look, this is one panel of the slab, and you have a kind of a curved distributed load or edge load, as you can see in the final configuration, and 2 point loads. So 2 point loads are available with the one, say, like a vertical wall. So we model the wall based on the corresponding load. So we need to know where is the position of that, where are the 2 points, we imprint them, and then you impose the load on the imprinted edge and points, and you go through the process of loading. You can manipulate the different edges, corners, you can extrude, flip, and also you can do some sort of extrusion, extract, and matching different, say, bodies with respect to each other. And if you have two bodies, you can always align and match them based on the coincident nodes, coplanar, parallel, and concentric configuration to match them and bring them to the common and touching points. With respect to the function, as I mentioned here, the function can be used in order to, for instance, in this particular case, in a very schematic way, you'll see that if I want to model this bridge with the shell, these shells at the abutment side are quite thick and the middle of the span is thin. So you can model this effect, excuse me, with the use of the function, and with the function you can define some sort of thickness in the outer part and the thin in the middle part, and you can combine this function also with other aspects like variation of the cohesion or Young modulus, or the temperature in depth, in the width, or in different dimensions. For instance, in this particular case, we have a water definition. This water definition can be done in 2D or 3D. So in 3D is kind of a surface and like piezometric positions. And in the 2D is kind of a profile of the water, and this profile can be introduced either as a function, you can specify the function in the corresponding field, or you can define some piecewise nodes, and that generates your profile for your water level. Another powerful tool that can be combined in Dana is the Python. So imagine if you want to optimize the geometry of your beam subjected to the load, and based on that you see what are the effective zones and areas in terms of using the reinforcement. You can use some geometry optimization algorithm, and when the model is subject to the load, you can see how these loads can be affected and optimized through certain location and position in the model. With respect to extrusion, and we are now trying to go towards meshing. So we have an extrusion shape, and this extrusion shape, it basically sends a signal for our extrusion measure that automatically triggers that feature in Dana. So in this particular case, I have a plate, and the model can be extruded based on the, say, the thickness direction, and you can see how easily this model can be extruded. And since this geometry inherits this extrusion process, our mesh engine automatically use the extrusion measure, and you have very nice and uniform mesh distribution or element distribution in the extrusion direction. Moreover, we have adaptive element option. This adaptive element option is important if you have some sort of a sharp change in the geometry or curved shapes. It helps you to increase the density of the nodes and elements in those areas to avoid a peak stress concentration in those zones. So in order to make a smooth transition of the internal variables, you may use this adaptive measure or option to define a denser nodes and elements in your model. So in this particular case, you can see the outer curve here when the model is off based on these adaptive seedings, and this one is when the model is on. So you see the number of the nodes and elements are more in this corner. Similarly, in a planar 3D, say it's Bezier surface, this is like a terrain model. So you can see if the model carries the adaptive seeding option on, so how the elements become fine in certain corners and the peaks and edges, and how the elements become coarse when that option is off. Another powerful tool that gets along with the meshing and helps you to define the topology and the arrangement of your elements in the model is our element grading or seeding. So this could be defined based on the size, based on the division, based on the, say, density distribution at the surface level. And you can combine all these effects to make sure that your model is optimized with respect to the mesh topology and analysis time, because if you define fine elements all over the model while there is no need to have such a high density elements, that's going to cost you time in terms of running the analysis. Therefore, you can always rearrange the position of these elements in the corner and the zones that are more often subjected to the construction or some, say, loading or manipulations. After meshing, you can visualize your line elements, 3D lines or 2D lines, based on the corresponding assigned sections. So if you have different profiles and you assign them as a kind of a line elements in your model, after meshing, you can see the position of them, the alignment of their beta angle, and you can make sure that they are located in a correct or the most strong direction that you want to be according to your model. At the mesh level, there are different view options are available. All are towards make your life easier, to have a better understanding about the different parts, especially in the 3D when there are lots of intersections, lots of embedded parts, and bodies are available. You may use different view options in order to clarify and visualize different part of the model to make sure everything is in place as it should be. These are some of the outputs for the measures with a nice hexadominant with a kind of a structured model and tetrahedron, say, dominant models. But as I mentioned, if you go through the iterative procedure, if you go to the parametric analysis, in order to save your time for meshing the model, we have adopted one technique called incremental meshing. This incremental meshing is at the element level, I mean the body level, and also for the embedded elements like reinforcement, piles, sheet piles, and all those things. So it automatically searches, it finds the parts that are modified, and it only remesh those small and individual parts and some adjacent and affected part. This way, you don't need to go for remeshing the whole model from A to Z. This is very powerful, very useful in order to save time and speed up your modeling process. Furthermore, all the information, material models, implementation, background theories, verification documents, all those things are available in our online documentations that you can freely go through them and study them in terms of how we implemented, adapted different aspects in Diana. With respect to analysis type, we have various types of analysis type: linear static, nonlinear, dynamic, general stability, potential flow, coupled flow stress analysis, and phase analysis. I go through them one by one. With respect to the linear static analysis, this gets along with the moving loads, with the fatigue analysis, with the general fracture mechanic analysis, with the design check analysis. These are all necessities that you may refer to them with respect to the linear static analysis. However, when you go one step further, you can introduce extra nonlinearity in the model, but this nonlinearity could be at the material level, could be geometrical nonlinear analysis, or the nonlinearity dependent on time. So you can combine also all these three aspects together. You can also use Diana with respect to the contact analysis. So the contact analysis here you can see is squeezing a disk, and this algorithm for finding a new contact surface is nonlinear, and the procedure is nonlinear. That's why it's categorized under the nonlinear analysis. For dynamic analysis, the seismic analysis, we have different type of solutions. Could be direct frequency, modal, or spectrum analysis. You can use Diana for linear and nonlinear time history analysis. The hybrid frequency time domain, that's automatically Diana converts based on fast Fourier transformation your domain from the time to frequency or frequency to domain. If you have a kind of model based on the two input in terms of the material properties, and we have a far field boundary elements in order to absorb the propagated wave in the model. Also, we have a PML implementation, perfectly matched layered, in order if the source of vibration or dynamics is on the top, if this wants to propagate in the domain, how this PML gonna absorb this propagation in the model. And also for transformation of the mass of the reservoir or fluid domain in the tank or in a reservoir of the dam or some dikes. You can use fluid structure interaction. This mass automatically gets transferred to the body, to the structure, and you can literally, as a consequence of the time series analysis, you can obtain the, say, the hydrodynamic pressure acting on the model. You can use Diana for general buckling, post-buckling, and also perturbation analysis and continuation analysis as well. For flow analysis, the flow could be heat flow analysis or groundwater flow analysis. If it is heat flow analysis, we are talking about different parameters like conduction, convection, and radiation. And if you're dealing with the groundwater flow, we are talking about just the flow and how this is going to deal with the permeability and the porosity and the pore pressure in the model. If you're dealing with the heat flow, we have temperature and time dependency at the material level, while we are dealing with the groundwater flow, we are talking about the permeability and the pore pressure dependency on the, say, permeability. In this category, we have a contamination transport in the pollutant medium. So if there are particles, you can perform the analysis and mimic how this, say, contamination is transferred in the model. And we have some mechanical solutions in terms of the movement of the bearings and the support and how this movement could induce heat in the model. With respect to the flow analysis, you need to couple that with the stress analysis, because when there is a heat, when there is a groundwater flow analysis, you want to see how this effect of the temperature gradient or cooling, or how the increase of the pore pressure or the decreasing of that is causing a deformation in the model. So Diana provides the platform that you could define this interaction as a fully coupled or semi-coupled analysis. For phase analysis, then offers two types of approach for phase analysis as a construction stage to erect and set up the model, or go for the decommissioning and the demolishing of the structure. Also, you can use phase analysis in conjunction with the flow analysis. So next to those conventional type of analysis, you can use Dana for random field analysis based on the introducing heterogeneity in the model, not homogeneity, stiffness adaptation, parameter estimation, probabilistic analysis, liquefaction analysis, and explicit time integration analysis that helps you to really extend and challenge all the high-end analysis from beginning to the end in one platform as Diana. We cover more than 250 elements based on the order of them, from the point element to the line to the surface to the solid, specific type of elements with respect to the mass element, spring interface, geotextile, and compose elements in a low order and high order formulation that can get along with our different types of analysis. Moreover, we offer embedded element concept. That this embedded element concept has advantage that you generate and you define the geometry of your elements. Could be the reinforcement, could be the pile, so there is no need for nodal connectivity. And you can use this concept in conjunction with the tendons, with conjunction with the reinforcement, grid reinforcement, individual bars, pile elements, pile tip elements, and also with respect to the sheet pile and anchors that we're going to talk in the later slides. The compose element is a very powerful virtual tool that helps you, especially if you're dealing with the design, if you're dealing with the kind of a checking, to convert and give you the sectional forces, moments, shears from the continuum model. So in the context of plane stress, if I have a beam and this beam is subject to the two loads on the top, these compose elements, one line in the middle, can give you some sort of output for the bending and shear associated to this continuum model. Similarly, is available in the 3D model and the composed surface. For the material model, we have about 150 constitutive models. They're all non-constitutive models that you can use and adapt them for different types of applications. Could be linear, non-linear, could be isotropic or orthotropic, and also viscoelasticity and viscoplasticity. For modeling the crack, these cracks could be discrete and smeared for considering of the effect of the creep and shrinkage based on the model code or based on the user-defined SAID functions. And all those material properties are available in the different categories, as I mentioned, at the class level and the material types. I briefly touch base on the some of the known ones, but the rest are available. We can discuss if it's needed. For crack model, you can use the discrete crack model if the crack is already apparent and you want to see how this crack is pinching, like opening and closing subjected to the loading. So in that case, you may use discrete cracking approach. But on the other hand, if you're dealing with a smeared crack model, that means your model is continuum, there is no damage, but you want to see if the crack is happening, from where it happens, how it initiates, how it propagates, how it goes through the failure. You can incorporate the material based on the model code, and you can introduce the fiber material model in the kind of concrete model. At the masonry level, we have engineering masonry model that helps you to introduce anisotropic cracking, crushing, and shear failure in the model, including some sort of a diagonal crack failure or staircase failure in the model. And this is very powerful and validated and verified model that you can use them when the masonry structure is subjected to cyclic load, because it's energy dependent implementation, and you can nicely see how this dissipation takes form in compared to the actual full-scale test or the lab results. Creep and shrinkage, as I mentioned, these are available based on the different criteria that we have, based on the model code, based on the user defined and the different characteristics and criteria that you may consider for modeling the creep and shrinkage in the model. You can interact and intersect different types of element types by means of spring and dashpots to mimic the interaction by means of linear behavior, nonlinear behavior, plastic spring, subgrade reactions, and nonlinear dampers that you may consider for bearings, for instance, when the bridge deck sits on the bridge pier cap. So all those things can be nicely modeled based on the advanced setup of the continuous damping that are available in the Dana environment. Moreover, the interface can help you to interact different parts by means of linear or nonlinear interaction, cracking, bond slip, Coulomb friction, CSC behavior, and the user-supplied subroutine. For reinforcement material model and the tendons in general, you can assign the linear behavior, plasticity, hysteretic behavior, and also for tendons you can consider the no bond or grouted part and also incorporate that with the user-supplied subroutine. For soil model, we have different concepts for stress initialization based on the stress field and based on the K-node procedure. You may consider the drain or undrain behavior and also variation of the phreatic surface in the model. This is a quick overview about the soil models and the available material model for the geotechnical application that you may refer to them. And for sheet pile analysis, as I mentioned, we have a concept of embedded element. This embedded element is available for the reinforcement. For the pile elements, that means your pile can be defined wherever they are without any effect on the overall ground elements. And we have a concept of sheet pile and anchors that I'm going to talk here about them. So for the sheet pile, it's very interesting because user can define a line in the context of 2D or a face in the context of 3D and assign a kind of a sheet pile property based on the different characteristics that I'm going to talk to these sheet pile elements. These sheet piles automatically carries the interface between the soil, adjacent soil, and the interaction of that can be introduced with different criteria. When the sheet pile is not active in the initialization, for instance, the phase of stress initialization, then automatically considers the homogeneity in the model. As soon as the sheet pile comes to the picture, the interface also gets activated along the sheet pile. For anchors, we have a free length and the grouted part. And the grouted part can be introduced by means of bond slip, and the generation and definition of these free length and the grouted length are in a wizard and automatic. Well, you can also define the water level. I will talk about them with the constant or with some sort of a dewatering. So this is very useful, especially when you go for the context of excavation. For the sheet pile, we have two definition. One is equivalent thickness cross-section and another one is generalized cross-section. If you're dealing with the equivalent thickness, then your inputs are based on the relative and generic material properties, while if you're dealing with the generalized cross-section, then you have access also to the library of the different sheet piles that I will tell you in the later slides. But your material properties is based on the sectional properties like EI and EA. In terms of the automatic generation of the interface, you have different characteristics. These could be linear or could be non-linear and automatically driven from the adjacent soil based on the reduction factor that you specify and you define in the wizard of sheet pile. If your sheet pile is designed to carry from the adjacent load, from the confined load, that's fine. But if you have some 20-30% of the bearing calculation for the sheet pile tip, you can activate that and specify the failure of the sheet pile tip as well. As I mentioned, if you go for the generalized cross-section, you have access to the library. This library is based on the ArcelorMittal database, based on the U section, Z section. You can choose different profile that you want, then automatically brings up all the necessary parameters and information, and you can just simply choose the section and go through the rest of the analysis. Then it retrieves all the parameters and the sectional properties and the dimensions associated to these sections. For anchors, you can define the bonded length. So for instance, if you have a 10, 20 meters, so you can say, okay, what would be the grouted part, if it is fully bonded or no. And in terms of the material properties, you can define your elastic parameters. And also for the grouted part, you can say if there is or the bonded slip part, what are the stiffnesses associated to that part, and what would be the bond slip failure mechanism that we are dealing with. And this is at the material level. At the geometry level, you need to specify what would be the cross section, what would be the, say, the spacing if you're dealing with the plane strain context, and some parameters associated to the geometry, either diameter or the cross section or the area. So I walk through one of the demos that we have here. You can still use the question box or chat box if you have any questions. So in this particular case, we set up a new analysis in context of plane strain with the quadratic elements. So the model gets initiated. And now I'm going to change the material units, the model units based on the kilonewton and meter. What we are going to do, we are going to define the soil state boundaries. The first one that we are going to define is the clay layer. The coordinates and the dimensions are available. I just copy and paste them in the corresponding dialog box. You can see I fit it and the corresponding clay is generated. We are going to define another layer, sand layer. The sand layer is the lower layer. So you can copy and paste and you can see the position of the lower part, the position of the upper part, and the right zone are set of the layers that I want to define during the excavation. So to this end, once again, what we are going to do, we are going to create different rectangles for the different excavation zones. So I call it clay excavation 1. That's the zone that here you can see in blue. I create that. We repeat the same for zone 2, the excavation zone 2, clay excavation 2. The coordinates can be easily, I use Excel here because I know the dimension just to speed up, just copy and paste them. You can do the same process. Otherwise, you can click from the working environment, or you can, if you have the coordinates, you can just copy and paste them in the model. So this is the second one. On the left side, you can see under the geometry, the corresponding geometry sections are automatically generated. Clay, sand, clay excavation 1, clay excavation 2, and this is the clay excavation 3. The coordinates get copied. Perfect. So here you see all these components, geometry components are generated. The next step is we are going to define a strut. This strut can be defined either by creating one line, or you can just simply extract the edge from the existing geometry. So I select, change the filter to edge, I extract that, and you can see this edge is generated there, and I change the name to strut. So perfect, we have all the main components for the excavation. So now we are going to create one line from top to bottom position of the sheet pile. So now I'm creating a geometry line associated to this, say, sheet pile. So you can see at the geometry level this sheet pile. To create the sheet pile, I click on the wizard, type sheet pile. In terms of the material that we're gonna deal in this demo, I leave it with the linear interface. So just for the demonstration, no pile tip. We click OK. So we keep it based on the equivalent thickness cross section. So I define the generic input for my Young modulus. To avoid Poisson effect, I leave it 0, and mass density for the weight or mass density of the sheet pile and the equivalent thickness that I already calculated. I click create. So you can see the sheet pile set is generated there based on those attributes. What I need to do, I just simply drag and drop my geometry sheet pile into corresponding set. Here we go. So now if I click there, you can see all the assigned properties to the sheet pile. It is very simple and very intuitive. Now we are going to literally define material properties. So I'm going to import material property for the soil from our database that I had earlier. So you can see material properties are nicely imported. Now I just need to select the upper soil layers. I ignore the strut. I assign the material based on the plane strain and the loam soil. I select the lower part and try to assign the same context, but this time the material property is sand. You can see that in the property window, everything is assigned correctly. Now we are going to do the same thing, but this time for a strut. So we select the corresponding element class and strut material properties. And from the geometry point of view, the geometry data, we're going to define the cross section and spacing that are associated for these struts. So we define some nominal spacing for out of plane, say it every 1 meter, and create. So now we have defined the material properties and the general properties to all the geometry components that we have. Everything is clear now. Then we are going to assign boundary conditions. So we have boundary conditions in the X and we assign them under the one global boundary set. So this support set, we call it BC as a boundary condition. We select the edges on the side and the bottom and constrain them in the X, create, and we repeat the same, but this time for the lower part, boundary condition Y, but again, they go to the same support set as a BC. So the support set BC carries up to now 2 boundary conditions. And for the strut, we're going to repeat the same, but in the symmetry direction, we only constrain it in the X direction. So we call a new BC strut, again under the same boundary conditions. This time we change the selection to the vertex. We select that, and in the X direction, create. Beautiful. So if I expand my support, you can see under the BC, I have all those support assigned. So maybe I can do this, and I think we can define a water table. So to avoid any conflict. So we hide the support. Now we have a water level. We have water level at two levels. One is when the water level is 15 meter at the top. The water level set is 15 meter. This complies with the whole model. In the function, we can see from the left side, when it's 0, the x is 0, the water level is 15 meter. And when the model is on the far right side at the center of the symmetry is 65, the water level is 15. So this is a constant line. And if I create, you can see the constant line appears there. The next water level is when we are going to dewater. So we're going to define a profile that varies and helps us to go to the bottom of the excavation and have a dry zone. So this time we define the water level as a 0 meter. So in terms of the profile now, okay, at 0 is 15, then this is start of the deviation and the dewatering profile at 25 meter, 50 and 65. So this is how, if I click create, this is how the profile of the dewatering gonna take form in the model. So we have two water level. One is 15 and another one when it's the dewatering level goes to 0. We mesh the model. We set up the stage construction based on the 5 stages, including initialization, excavations. And when we run the model, we can see the results. We start with the stress initialization, the horizontal stress and the vertical stress in the X and Y dimension, the deformed, undeformed view. We can go through the whole process of excavation, activation of the strut, and final excavation. We can see the force that is acting in the strut and the installation, and after that, as it goes through the excavation, the force becomes more active. For sheet pile, you can see the axial force, how it gets developed. If we go from the phase 2 that we install the activation, we install the sheet pile. As we go through, you can see how NX axial force is evolving. Similarly for the bending, if I go for the position of installation and go through the excavation, you see how the bending is forming in the model. Moreover, we can discuss about the pressure head. If we go to counter, so at the beginning, when the water level was 18, the lower part is 30 and then 15 meter height, so altogether become 45. That's the pressure head, and this is when we have a dewatering. So you see how this follows the profile that we introduce into the system. The same effect also can be investigated for the sheet pile on the negative side and the positive side, or say it on the side of excavation or on the side of the continuity. So this was a quick overview. More than whatever we discuss about the existing material models, we have a possibility of adapting user supply subroutines, so you can write your own constitutive model and assign it at different levels to the model and use it in conjunction with the other tools that we have in Diana. For load and boundary conditions, you may already saw some, but we have a complete coverage of the nodal, concentrated, distributed, quadrilateral loads as a kind of arbitrary loads, and a combination of the different type of constraint in conjunction with the functions. And you can assign them to the geometry and see the impact and effect of that on the final model. The input, which are in a tabular format, they're compatible with Excel, so you can always copy and paste from Excel to Dana or from Dana to Excel for any manipulation and further, say, visualization. If you get output, the output can be visualized based on the tabular output, based on the plot, and also based on the contour. These are very powerful, very nice, and you can tag them where the maximum and minimum of the selected results are in the model. If you cut the model, you can see the corresponding edge for the cut edge, so it's not vague or faded, so you can nicely see the position of the slicing and cutting plane. And also you can take advantage of mirror option. This is very powerful if you're dealing with the symmetry, quarter symmetry. In order to speed up your analysis, you can model your quarter symmetry, you can model your symmetry model, and then in the post-processing you can mirror it, you can visualize it, you can do the animation for the mirrored model. And also we have a Sage report generator. This report generator is possible based on the different setups, different say the layout that you can define, and the different output that you can specify and get in the after the analysis in the model. We have different solution procedures. This could be linear equation solver, nonlinear equation solver, and eigenvalue solver. That depends on the complexity. You can take benefit of the parallel processing, or you can leave based on the optimized settings that we Dana defined in the at the solver level. For nonlinear analysis, we have different iterative procedures. We have different incremental procedure that all are empowered with the advanced and optimized algorithm in order to capture the best and unique solutions and available solutions for your model. As I mentioned, Python scripting is powerful. Try to take benefit of that. You can use the syntaxes and script associated to that and use that in conjunction with building your model or extracting the results or generating the report. These are the platforms that based on the 64-bit and based on the Linux and the Windows are available. And for the quality assurance, as I mentioned, every night we go over the more than 10,000 unit tests in order to assure the quality and accuracy of the implementations. About 5,000 of them are available in the installation shield. So if you have a Dana, you already have 5,000 of them in your installation, and you can see and check and test them. And this is automatic regression test that helps the developers to keep the quality up to the expectation. So I would like to thank you all for attending this session and wish you a pleasant day. Thank you. Bye.